First person speaking is Brad Fidler. Brad, you want to come up? Brad's a researcher with the UCLA Computer Science Department and a visiting research scholar with the USC Information Sciences Institute. He studies the history and politics of internet and cybersecurity infrastructure, architecture, and governance. He's active in the history of technology, history of computing, and science and technology studies, or STS, for those of you who don't know what that is. And he contributes to the digital humanities. Wrote his doctoral dissertation at UCLA in history in 2011 on market strategy for atypical antipsychotics. And you probably knew I was going to say that.
All right. Thank you, Andy. Right, so my talk today is on routing architectures and social and power relations. And in particular, I'm talking about this thing called routing architecture, which I will define. Which I think is an interesting way to talk about infrastructure, to talk about different kinds of infrastructures and their links that they have with one another through an understanding of their routing architecture. This is an interesting way to talk about both transportation and communication infrastructure, although I'm really going to be focusing on communication today. So yeah, in addition to drawing links between infrastructures that would formally be considered disconnected or separate, it's also, routing architecture is also a useful and interesting way to talk about the mutual determination or like overlapping fields, choose your metaphor, of the social and the technological. My first point is that this thing called the end-to-end principle. How many people have come across the end-to-end principle in their lives? Some of you. So just very briefly, I want to make a point that it's not for us as a methodological strategy or an epistemic claim. The end-to-end principle is this doctrine, an ideology, if you follow Andy's research on this, that says that whatever kind of services you want to put into a computer network, for example, error correction or something like that, you're still going to need to have the ends of the network, the computers that are connected to it on both sides of the communication link. They're still going to need to double check what the network does for themselves, so you're going to end up duplicating functions. And as a consequence, it's more efficient if you just put as much as you can into the ends of the network and leave the network as dumb as possible. And a corollary to this is that the users then also get more freedom to do the kinds of things they want to do on the network. And that is a very useful strategy in computer science and computer networking. For social science and humanities researchers, there's been a tendency, I think, to do very important work, but to really focus on the ends of these networks. So looking at the software on my computer, looking at Facebook servers, things that happen on both ends of a connection over a network, and a kind of oversight as to what's actually going on in these networks themselves. One of the consequences of this is that it's hard to speak historically and analytically about changes, for example, in the structure of the internet between, in this case, 1982 and a couple months ago. TCP and IP, these protocols that we've heard a lot about that run the internet, parts of it, have changed very little, but what's actually changed a lot is this routing architecture, this broader structure of the internet. It also provides a way to, speaking more to routing architecture as a concept, you can maybe draw links between routing in traffic, this kind of traffic, and the kind of traffic on the internet, and other kinds of distribution networks that are also prone to failure. Another reason that I find compelling to talk about this is that the modern social sciences, for better or worse, started off in part through a kind of negotiation, an interrogation of the relationship between labor and the infrastructures of the day. So what does it mean to be a laborer in a factory, for example? We might do a similar thing with the infrastructures that are, this part of the information infrastructures that are in turn driving revolutions in our own era. And finally, talking about routing is an interesting way to be able to look at one of these when you go home tonight and you see your router and say, oh, what is this? More than just something that you're always resetting, maybe we can say this is a historical object, this is a political object, this is something that we can speak about in terms of histories and politics of information and computing. So as a quick stab, as a shorthand definition of what a routing architecture might be, it gets thrown around a bit in computer science, but rarely defined. And I'm making a kind of a broader definition that I use. I have a paper coming out on some of this stuff quite soon. And I'll go through some of the points here. When I say routing architecture has components of a socio-technical system, as I will go into some detail later, there are not just technologies, but also humans and institutions, political organizations involved in this, so it's a socio-technical. When I say that it identifies and then selects part of a routing architecture is a system of identification of addressing, so a kind of set of epistemic claims built in. And when I say select internode paths, what I'm referring to here is that unlike, for example, actor network theory or some kind of material semiotic method, this is actually structuralist. There are nodes and paths between those nodes that are there to stay, at least for a while, and it's about selecting from within an existing structure. And so as I alluded to there, it's not actor network theory, it's not social network analysis, it's actually an analysis of existing infrastructures. We'll get into some of the actual additional kind of components that are in routing infrastructures, routing architectures rather. I'll be alluding to there's typically a process where knowledge about the architecture is generated, so which nodes are connected to which other nodes, and then there's a system of figuring out the best way to calculate routes between them. If politics is who gets what and how, we might think about a routing architecture as what gets where and how, and to what resource cost and whatnot. Some claims about the power of this concept, of the usefulness, the utility. Routing architectures will structure communication in particular ways. They will presuppose, reinforce, and restructure labor relations. So they presuppose certain power relations in the socio-technical pieces of these architectures. I'm going to argue that they exist in connected historical lineages, and you'll see what I mean in a moment. I think if you make claims that something has a kind of complex relationship with, for example, labor and broad social relations, it's unlikely that these things will simply change when a new idea shows up. That it's probably more of a historical process, how these architectures shift in different infrastructures over time. When I was doing this work this follows out of my work on routing and routing algorithms on the internet, I was reminded of a question that this fellow named Bjorn Westergaard asked me at SIGSIS in 2014. He was going to be here, but he's not. And he asked me, and he asked some other people. He was doing some primary source research, and he said, did foundational work in packet switching and queuing theory, I'll get to that in a minute, reflect labor practices from that era's communication systems? So packet switching, how many people have come across that term in their lives? Yeah, we've heard of this. This is the idea that you break up information into discrete packets, and then those packets can be routed independently or semi-independently throughout a network, lots of efficiency gains, foundation of the internet from some perspectives. And he was curious if this reflected, when for example, Paul Barron was doing his seminal work on packet switching, did this just reflect things was this a codification of existing labor relations in other kinds of, for example, communication infrastructure? And I'm taking a slightly different approach to this question because I see packet switching as kind of an intellectual history where as I have interviewed some of the people that were developing routing algorithms for the early packet switch networks, they were only marginally aware of this kind of seminal work in packet switching. They were really just building what made sense in this kind of this professional cultural environment. And I think it's, for me as a starting point, more useful to look at relationships between actually existing systems of practices and how those hop between infrastructures, perhaps. So I'm going to make a kind of, just by looking at routing architecture and using that as kind of an analytical framework, I'm going to compare the telegraph to this network called the ARPANET, and then this other larger network of networks called the Internet. The ARPANET, just very briefly, was a general purpose packet switch network that became the first backbone of the Internet in the early 1980s. Now this, we have a comparison of header metadata. So that's a telegram on the left from a system that was in place in the 1950s, although this metadata structure goes back to the early 20th century, and you can see that like the header metadata of an internet protocol packet, you have source and destination addressing, and you also have a way to identify in this case, the telegram against other telegrams that are being sent, for example, immediately before and after it. So there's a kind of an interesting similarity there, but moreover, this is a comparison of topologies between this is another kind of iteration of Western Union's American Telegraph Network. This is an ideal type of the topology. It didn't look exactly like this, but it wasn't entirely different. Similarly, this is a kind of an ideal type of the ARPANET topology. And there's a bunch of looking at how routing worked in these two systems, there's a bunch of interesting similarities that show up. In the telegraph network, for example, messages are routed independently, hop by hop, based on a destination address, which is something that we associate with this thing called a datagram or packet switching today. On these telegraph networks, there was adaptive routing. So there were routing tables. I'll show you some of them in a minute. If one of the telegraph centers broke or a line went down, they had adaptive, alternate routes ready to go. So things could, you could route around damage. There were other small things like before a telegram would be sent from one node to the next, there was a system to check ahead to make sure that there was space at the person or machine that would be accepting it. And the fairly decentralized topology of the telegraph system, much like the early ARPANET, was based on a kind of ongoing assessment of traffic loads and how the topology would be modified to be the most effective. So there was, and finally, there was also a terrible metaphorical baggage. So the one on the left was a speedway for words in the early 1950s. So there's these bad metaphors. That's another point of comparison. So, and I haven't seen speedway for words discussed that much, but that's what Western Union was calling their telegraph system. And of course, the attendant promises of space and time obliteration. So this is a routing clerk, and what's interesting is that the routing, the kind of some brief details of that routing architecture of the telegraph system that look a lot like the ARPANET and then Internet were developed before even really electromechanical automation of telegraph switching. This was developed when the routing work, for example, was done by people, and with the civilian telegraph network in the United States, it was almost entirely women. So I have to stay here. The papers on the left, that's a routing table. Lois Christ is checking the routing table. She probably has a lot of it memorized, and she's probably thinking that if she just checks it like the photographer is asking her to, he will go away and she can get back to work. But this is the labor that was at the heart of the telegraph network, and this kind of fundamental relationship around which that routing architecture developed. There is a fair bit of work on especially the American telegraph networks, and I'm not going to get into too much detail here, but suffice to say there's a lot of really interesting work. It starts with things from 150 years ago that could have been published last year, 150 years. History, theory, and the practice of whatever. at CSIS. We're still going strong, half a century and a half later. But then there's been a whole bunch of more recent work, and it's all very interesting. There hasn't been, I think, a lot of effort to look at the exact routing mechanism with an interest to how this might connect to later infrastructures, and maybe to start talking about a broader, longer historical lineage that includes the internet, the ARPANET, related networks, and the telegraph network as part of this kind of broader, very similar and in some kind of lineage being at work. One of the interesting points is that this is someone manning a packet switch for a military telegraph network, Autodin. That was almost entirely men. In the civilian telegraph networks, it was almost entirely women, so you'd be having a hard time making kind of culturalist excuses for that gender balance without actually just appealing to very explicit like institutional and political structures that would explain it. Here's actually another picture of routing clerks or routers at work. And this is a routing table, a modification to a routing table being put up for the day. And a routing table would be, just to clarify that point, if you, I'll explain it when I get to, let's talk about it here. One of the challenges, the main challenge of a network like this telegraph network, like the ARPANET and like the internet, is that there's a distributed set of nodes, right? And they all have to follow a certain kind of logic. They have to follow what's now called an algorithm, or previously a doctrine or a procedure, and they should all be following the same kind of one so that the system works as a distributed computation to get telegraphs or packets through it. And you have to not only have everyone using the same procedure or doctrine, but you also have to have it implemented faithfully and appropriately, otherwise the system doesn't work. One of the examples with the ARPANET and the internet is that a router will be responsible for telling nearby routers who it's connected to and what are the best paths that it can be a part of based on where it is vis-a-vis its neighbors. That challenge, that assumption of a kind of centralized authority in all of these systems is something that keeps breaking down and won't stop breaking down, because no matter how decentralized you try to make your communication infrastructure, the more decentralized your routers are going to be, the more you rely on a centralized authority to make sure that they're all behaving the same way. And I've got an example of three. In closing, I'll give you an example of what I mean. There are three kind of case studies of failures that are the same kind of failure that we haven't really been able to stamp out. The first was a misrouted message to the USS Liberty to go somewhere else in 1967, which it never got because a routing clerk routed a message the wrong way. It stayed in a part of the ocean it shouldn't, and it got torpedoed by Israelis during the war in 1967, and 30-something people died. Far less serious, but the same kind of problem on the ARPANET in 1973. The Harvard router had a memory glitch and broadcast to everyone nearby that it was the closest route to everywhere. It was 0 hops from every single place in the network, which a joke from Lee Vinzel from last week is Harvard's still telling everyone that. All the traffic went there and it crashed. The same thing happened with Pakistan Telecom telling everyone it was the closest route to YouTube in 2008. Same problem. YouTube disappeared for a number of hours. So there's, in the kind of shifts of infrastructures that we would assume to be kind of different, looking at the routing architecture that they have and the kinds of assumptions, not only about the kind of management that must exist below, but then also the relationship with the people who are doing the routing or the people who are encoding the software that does the routing below, it allows us to see lineages and it allows us to see connections that we may have otherwise missed. To historicize the end-to-end principle, which I promised in my subtitle months ago, and I'm kind of doing a little less now, the end-to-end principle then looking at it historically would be it's a specific relationship with a kind of labor and the ability to either black box it or just not address it in whatever kind of work one might be doing. Thank you.
There's this thing that happens when you're living on the East Coast of the United States of America and talk to your peers about Silicon Valley, is that when they say the word Silicon Valley, they say it as though they are like conjuring a demon that is here to like consume society, rather than talking about a place, right, with a kind of historical specificity and geography and contingencies that kind of shape that industry as much as like whole earth catalogs and Xerox PARC beanbag chairs do, right? And I'm going to be talking a little bit about that history, which, to be fair, as like, you know, a sullen teen, I took for granted and did not spend that much time around, but that I've found useful in thinking about other work that I do. And this is a place in Silicon Valley that I find very useful for kind of illustrating this story. This is a parking lot on Charleston Road. It's on the other side of the 101. Are there any little Valley folks around who will appreciate? Anyway. This is, people may have actually made pilgrimages to this site in this room. This is the commemorative plaque on 844 East Charleston Road that marks where Fairchild Semiconductor created the first commercially practicable integrated circuit, has the IEEE plaque and a State of California plaque. And then this is a document called the Restrictive Covenant. It's a document that explains all of the things you can't do at 844 East Charleston Road, like you can't build a school or a hospital or like an old folks home, because the groundwater underneath the property has been contaminated with solvents used in the semiconductor manufacture process. And this is a history that I imagine a lot of people are fairly familiar with, right? There are 22 Superfund sites in Santa Clara County. 19 of them are from the electronics industry. All of this is this has been documented. There's countless other ones that are of this scale. Like, this is not a federal Superfund site. It's a state-level cleanup project, and there are a lot of state-level cleanup projects as well. And I guess my interest in it is not necessarily to treat it as kind of like once again, as sort of like a footnote of this history, or kind of an accusation to kind of throw at computer history, so much as trying to understand, like, why is this not already there, and what has its absence sort of facilitated or enabled? This is the closest you get to a commemorative plaque for that particular history. And I've spent a lot of time thinking about commemorative plaques for these sites to little momentum. But so a little bit more kind of about what got me to go back to this history, because, you know, why would I go back to Palo Alto? So my background, I do make a lot of work around place. I make a lot of work around landscapes and the specific physical environments that are part of living in a networked world. My book is a field guide to finding the internet on the street, using quotidian elements of, you know, everyday urban environment to talk about telecommunications history and surveillance and urban planning and things related to kind of, again, living in a networked world. I also am an educator. I have a project with my collaborator, Surya Matu, developing teaching tools and curriculum for teaching children and young adults about some of the like kind of low-level protocol and infrastructural parts of the internet that are typically not really part of like traditional digital literacy initiatives. That's Surya and some adorable children who are way more into a fiber optic cable than I thought we could get them to be. And I introduced this particular kind of part of my work because I kind of just want to explain like the thing that I am often running against or trying to figure out how to challenge, which is a kind of facile analysis that I don't know if people here have like experienced having this kind of conversation with people about what they're doing. And luckily, you are not that audience. You are all very smart people. I'm very humbled to be in front of you. How am I doing on time? Cool. Okay, cool. So the reason that for the purposes of today, the reason that I kind of, what irks me about this particular kind of sudden realization that there is materiality to the internet is the misunderstanding that this is new, right? That all of a sudden, as software has eaten the world, it has also eaten industrial infrastructure, and it's unprecedented. And there are some things that are like unusual and weird. Like, it is actually, I think, kind of weird that Facebook and Microsoft and Google have been investing in submarine cables. Like, that was the purview of telecoms. That is kind of interesting. It also is interesting that these same companies are basically building parallel power grids. To some extent, this is a PR move and or a thing to get Greenpeace off of their backs, but it is also kind of about centralizing control, right? Like the fact that you kind of, it's the same reason that Goldman Sachs was the only place that had power after Hurricane Sandy. But simultaneously, there is this other tendency that I've noticed, which is part of the thing seeming new, which is software companies are owning their infrastructural identity in this really interesting way. 12 years ago, if you were trying to even get Google to admit they had data centers, it was kind of a challenge. And now they publish beautiful, magnificent photographs of this infrastructural sublime that is entirely kind of crafted by them and that is very much about like being on Google's particular terms and usually has very few humans. And if they're humans, they're like quite heroic. This is perhaps, and parallel to this sort of like charismatic mega infra, like welcoming of the data center as object, you have this rhetorical invoking of infrastructure in a way that maybe I just notice it more because that's a word that comes up a lot in my world, but that I think it's kind of interesting and compelling. Like, so this is Mark Zuckerberg's letter to the world after the election, where he invokes the phrase social infrastructure 15 times without ever explaining what social infrastructure is. He kind of got into using infrastructure as a word like right before the IPO, and there's sort of a self-fulfilling prophecy quality to that term, right? Like, I don't know, the social infrastructure of Facebook, I feel like, is as to AT&T's natural monopoly. Like, it becomes so the more you kind of demand that that is how the world shall be. Simultaneously, as infrastructure is kind of marshaled to this rhetorical ends and turned into this sort of like propaganda instrument, this innovation still exists in the pastoral landscape. This is the Frank Gehry designed Facebook building at the edge of Menlo Park. Like, I always just want to say it's East Palo Alto, but be that as it may. And this particular landscape, the idea of sort of the corporate office campus environment where all of your needs are met, is something that I think is often more what, when my peers who think that Silicon Valley is an ideology and not a landscape are imagining Silicon Valley, this is kind of the place they envision. And this is sort of a landscape that was perfected and cultivated in large part, like, deliberately, right? Like, the Stanford Industrial Park was created in 1951 to lure high technology firms to the region. And it did so also with a very specific kind of aesthetic end goal, right? Because the industrial park was supposed to look as non-industrial as humanly possible. It was supposed to kind of remove and obscure as much of that particular kind of accoutrement. Buildings couldn't be more than 2 stories tall. There were basically rules about sort of how you would arrange foliage to hide electrical equipment. Most significantly, to the Superfund sites, chemical tanks had to be hidden in some capacity, and they often were buried underground, and they leaked into the groundwater aquifers and into drinking waters. And there's a phrase that John Finley uses found in a document that he quotes in Magic Lands, his book on Western landscapes, where there was a planning document described that the thing they were trying to lure to the Stanford Industrial Park was light industry of a non-nuisance type. That also would attract what I think is referred to as a better class of workers. And when I first saw that phrase, light industry of a non-nuisance type, I got really excited because it seems sort of poetic and prophetic at the same time, right? Because to some extent, what has been afforded by the, office complexes of Silicon Valley is an industry and a society that is entirely contingent on the secure transmission of light through, strands of glass. To some extent, if Mark Andreessen had any sense of poetry, he might have not said that software was eating the world, but that we are all consumed by light industry. But maybe there's not enough room in the world for poetics. Generally, when we're talking about light industry, we're actually talking about things like this. We're talking about small-scale manufacturing. Well, not even small scale. It's still at a large kind of quantity. It's mostly just kind of like whether or not you have to lift heavy things or whether you can visibly tell that something is killing you, which you couldn't actually in a lot of these settings. I think it's hard to, I think it's important not to underestimate how much of the foundations of this region were manufacturing and the extent to which the manufacturing workforce actually built this place much more than some guys in a lab with cool ideas. No offense. And these are numbers that I found in a document from the Santa Clara County Occupational Safety and Health Organization, which was basically a worker organizing support center that did things like had a hotline for helping people find out what they were being exposed to on the job and reporting unsafe work conditions. They also did a lot of like consciousness raising stuff. This is a zine called My First Job, Meditations on Capitalism. And these are, it's really good. It's actually, if you have the time, San Jose State Archives, really great place. And so most of the people working in these like manufacturing environments did not know what they were being exposed to. Were not being told and were not being given like clear safety precautions. And one of the things kind of digging through these not very well organized archives, I've told that the person who was working on them quit halfway through, is the weird parallels and echoes of the so-called toxic culture associated with the Valley today appearing in the literally toxic culture of manufacturing of the 1970s and 80s. So for instance, the inability to kind of view the systemic quality of the problem. In a letter to the EPA, Congressman Norman Mineta, who represented San Jose at the time, was initially in the 80s demanding that the EPA label the entire Santa Clara Valley region a Superfund site. There were 120 sites that they wanted on the federal priorities list, and they were asking for this during Reagan, so like, come on, this isn't gonna happen. But I think that the reason that they were doing that is because rather than trying to understand this issue as a matter of like a few isolated actors who had damaged some part, like the way that aquifer contamination works, it travels, right? And it's like actually a matter of things like getting into the atmosphere and other things like that. And I don't know, it's really hard to go through those sorts of documents and not kind of be reminded of the like, it's not just Uber discourse and the tendency to try and identify the problems in Silicon Valley culture with single particularly bad companies as opposed to a systemic dilemma. Simultaneously, proving that there is in fact a systemic harm in the context of like particular bad actors is really hard. Like workers proving that specific chemicals were the ones that were making them sick is really, really hard to do because forensic truth is really difficult to prove, especially when you have an industry that doesn't necessarily want to do the studies to find out whether or not the things that they're exposing you to might give you cancer. And to their credit, a lot of these conditions have improved. Many of them have also just moved to other countries that have different and less regulations. I'm trying to remember, why did I include this one? So, like kind of the third layer of like weird parallels is the extent to which this all kind of becomes a cost of doing business, right? Like, oh, well, we have to kind of live with Facebook being a thing we kind of engage with, and there's no kind of other option for existing. In congressional testimony from hearings that were held with like the Public Works, what is that called in Congress? Committee. There is a really great part where basically people from Fairchild are arguing about what, like, the problem of, like, how clean is clean, and being really frustrated at how high or how low the parts per billion expectation of, like, a non-toxic exposure level is, as opposed to saying, like, maybe we shouldn't, have done this in the first place. Also, just side note, why men resent fast-track women? San Jose Mercury News, 1983. Who knows? I wish I could know. This is how am I doing?
You have 6.
Great, okay. So the ways in which this particular legacy kind of lives on in the landscape is certainly not as glorious as a magnificent data center. These are, and they kind of follow the same pattern of having to kind of obscure industrial architecture in various ways as they have since 1951. These are groundwater pumps at the Siemens Superfund site in Cupertino. That is the new Apple campus, which is what you can see when you stand in front of the groundwater pumps. And it's a very hard problem to see. And my background is in art, and I've been trying to kind of find good examples of interventions with this particular material, and have been, some of it has been really compelling, but it's also a little bit frustrating. So in 2006, Future Farmers, who are collective based in California, did a project called Gardening Superfund Sites, which was more of a speculative proposal to plant native wildlife and do reclamation on some of these locations. This is like a thing for like pressing plants that also had an archive. They did a bus tour of the sites, which is a trope that kind of comes up a lot. Silicon Monuments is a project by Elliot Anderson where he made an augmented reality app to try and introduce this like other history onto the landscapes. And I appreciate these particular projects a lot, but I also worry about the ways in which they continue to make it exceptional as opposed to kind of part of the entire narrative, right? Like, I just want a plaque next to the IEEE plaque. The idea that this stuff is not already inherently part of the history, I think, is where I'm still at. You know, the fact that one of these is in a vitrine in a History of Technology museum, and one of these is in a folder in an incomplete archive in San Jose, is disappointing and kind of a problem. And I'm not sure that I'm particularly well positioned to fix it beyond, you know, illegally installing some plaques, but that's more or less where I'm at. Thank you.
Our next speaker is Meredith Sattler. Meredith is an assistant professor of architecture at Cal Poly San Luis Obispo and is, I meant to ask you about this, simultaneously a Ph.D. student at the Virginia Tech Washington Alexandria Architecture Center and a lead BD+C. So she's busy. Her current research and teaching interests include conceptualizations of dynamic, sustainable architectural systems in historic and current contexts, interdisciplinary structure and practice within functional territories between design and ecological sciences, and the designer's influence on the health of natural environment, technology, human interactions. In other words, it's pretty closely related, I think, to what we just heard.
Thank you very much. It's great to be here. And I want to thank my fellow presenters and the conference organizers for a fantastic event. Like Ingrid, I'm a bit of an outsider, so please bear with me. And I do not have a background in computational history and came through this via architecture and environmental studies with recently some STS starting to invade the mix. And I'm really interested in material and environmental logics and how code is generative of physical manifestations and relationships between processes and productions of hybrid virtual physical worlds. And I'm also a little nervous about getting interrupted by ZZ Top. So great, okay, good. So I am gonna read, and here we go. So in 1978, enlisted Army, Navy, and Marine Corps personnel and their families began moving into the newly constructed Alumanu Valley Community for Military Family Housing, which was set within an inactive volcanic caldera near Pearl Harbor, Hawaii. Aside from its somewhat unique site, this 542-acre, 2,600 residential unit development appeared similar to countless other suburban hillside communities constructed in the US between the 1950s and the 1980s. What was illegible from examination of the final product was the key to its design and development. Alumanu was one of the first large-scale built communities designed, or I would argue co-produced, using computation. 7 years earlier, the San Francisco-based architecture firm of Willis and Associates began innovating a rigorous, computerized approach to residential land analysis, a hybrid digital analog workflow affectionately referred to as CARLA. Coded within Beverly Willis's office, it was, and there's Beverly on the right, it was designed to optimize the environmentally sensitive design and cost of large-scale residential development within challenging hilltop slopes. But CARLA's emergence was not as calculated or deterministic as it might initially appear. It converged in response to an entanglement of American cultural crises, largely contingent upon the confluence of novel environmental policy, economic depression, and the dawn of computer-assisted overlay mapping. Each year in the early 1970s brought increasing economic, political, and environmental strife to America, which had grave implications for the practice of architecture. In 1970, novel environmental regulation at the federal, the National Environmental Policy Act, or NEPA, and the EPA were founded, and at the state level, California's Environmental Quality Act, CEQA, were astonishing in their ambition and scope and provided challenging regulatory cocktails that were problematic to implement and enforce, particularly for built environment professionals. In Willis's office, quote, 6 of our major multifamily projects were put on hold by the California legislation. To avoid bankruptcy and to get permits for our projects, I met with state officials and learned they had not developed guidelines by which to evaluate projects like mine. It was clear that the Act's implications for the planning and development industry were incompatible with current workflows. So Willis's initial pro bono relationship with state officials, so Willis initiated a pro bono relationship with state officials to contribute to the development of urgently needed protocols, which ultimately became the Environmental Impact Assessment, or EAI, administrative procedures. She soon became head of the Facility Council. At the time, Willis lacked the comprehensive environmental knowledge necessary to ensure that overarching CEQA goals remain intact through the process. After a full day's work in the office, she spent evenings immersed in the study of geology, biology, ecology, and economics to better understand the larger picture of CEQA's intent. Her design philosophy would crystallize these diverse disciplines within a multi-scalar process linking the intimacy of home to the street to the environment through a systemic approach. Years later, she stated, "The various participants in the environmental design profession tend to look myopically at the system's elements and see only the parts within their own sphere of activity. However, each has an impact on the other. Because of this myopic viewpoint, sometimes various elements work against each other. This often hampers and restricts environmental protection rather than enhancing and protecting it." As part of her work with the state, Willis began diagramming CEQA's implications on architectural workflows, both from the perspectives of the designer and the regulator. These diagrams, which eventually took the form of systemic algorithms, became not only a tool for clear communication, but a shared language, and ultimately a habit of mind within the office. Soon they would facilitate the development of CARLA and have a profound effect on the firm's production and scope of services. WAI developed internal office procedures for authoring EIRs and included them within the scope of their work, both at the initiation of their projects and also as a standalone service. On the surface, the EIA work was a novel product in the market space, generating additional revenue and notoriety for the firm. It also facilitated immediate state permitting approvals of WAI projects. Critical to the development was a programmer and a WAI intern of sorts from Harvard University, Jochen Eigen, who will be officially introduced shortly. The analytical framework he and Willis developed went well above and beyond CEQA's regulation requirements. It included analysis of feedbacks between 63 environmental issues assembled into a comprehensive evaluation matrix from which each element would be analyzed in relation to the whole. Quote, "The form of document makes it evident that each planning variable, such as grading, has an impact on many environmental variables, i.e. landforms, slope, stability, erosion potential, wildlife, vegetation, health and safety, sensory perception, identity, etc. And conversely, each environmental variable, erosion, is affected by many planning variables, grading, tree removal, paving, landscape, drainage, etc. With this new environmental capacity, Willis realized she could leverage the then current economic strength of housing starts by providing environmentally based consulting and design services targeted at large suburban residential developers building on challenging sites. The tension between, quote, "every family's right to own a piece of the American dream and the threat of landsides, the residential ills and the heartbreak hills of California, had consistently claimed lives and property since 1945, yet development continued at a rampant pace. In 1971, housing starts reached a rate of 2.3 million units, their highest level in the post-war period. Simultaneously, non-residential construction was declining and unemployment was rising. In 73, the oil embargo, in combination with already skyrocketing inflation, created a perfect economic storm that brought the construction industry, along with most others, to a screeching halt. From 1970 to 72, Willis's firm averaged approximately 40 projects per year. In 73, they were down to 19, and by 74, they bottomed out at 8. Willis was keenly aware of her firm's and the nation's increasing economic vulnerability and struggled to attract enough clients to keep her employees working. As planners and policymakers were having difficulty coordinating the new environmental regulation, it remained up to private developers to determine how much risk they were willing to take on. In response, WAI, quote, "needed a way to evaluate and document vast acreage to determine the locations of environmentally sensitive land, unstable soils and natural drainage, and to forecast environmentally what would happen when we built on such land. This required new multi-scalar models for spatial mapping and analysis in order to fully integrate into the firm's architectural design process." Willis looked to current advances in computation. She knew that SOM, which was and still is a very large architecture firm, was using computation for human resource management and financial evaluation, but she was unaware of any firms using computation for design. Willis, quote, "envisioned a computer program that would allow me and my firm to solve the most difficult challenges facing the land planner, particularly construction on hillside slopes that involved substantial cut and fill land areas. I became aware of the plotting system McDonnell Douglas first created for WW2 bombers and located the exact target." She then, in 1970, found this version of the software at the Kansas State Geological School. It had been updated for use of searching out potential oil fields. I negotiated terms for its use in our CARLA program. At the time, computational spatial mapping and analysis was relatively new and primarily utilized for two-dimensional work. In the early 1970s, only large corporations, government entities, and universities were in the field. Developing software for private use was ambitious and costly. In addition, not only was digitizing and plotting maps a software-hardware challenge, but it required coding to perform spatial analysis was an entirely other order of magnitude. Expertise in the most current hardware and software was necessary, but it needed to be coupled with an understanding of the capabilities and limits of each and how to effectively integrate them into a larger architectural workflow. In 1969, Ian McHarg, a landscape architect and founder of the department at the University of Pennsylvania, published a book whose influence cannot be overstated, Design with Nature. In it, he introduced his map overlay methodology that combined quantitative geospatial data into comprehensive versions of causal landscape forces and chronological change through time. A method for determining land use suitability based on hierarchies of features, it was novel in that it operated both as an analytical and generative tool, key for Willis's production. Willis knew she needed a team with which to construct McHarg's process as her own version and vision of a computational land planning design process. She looked to Harvard's Laboratory for Computer Graphics and Spatial Analysis, which by this time was part of the Graduate School of Design at Harvard. WAI leveraged two individuals from Harvard that were critical in conceptualizing, coding, and implementing CARLA, Eric Tickholtz and Jochen Eigen. Tickholtz, who started at Harvard as an undergraduate in '68 and eventually became a professor and associate director of the lab, spent his MArch degree working in the basement of the lab in order to circumvent the school's subjective critical culture. After graduation, he stayed on until 1982 at the lab. But during the 1970s, he invented computational perspectival visualization, came up with the lab's logo, which you can see on the right, and kind of his design process, among other things. WAI employed him as a consultant as an as-needed basis throughout most of the 70s. Jochen Eigen, who was mentioned earlier, was a smart, attractive German exchange student who told it like it was. Upon his arrival at Harvard, he was unpleasantly surprised by the pedagogy and culture of the school. After a series of mishaps, including writing and releasing software that allowed students to anonymously grade their faculty, then distribute the results to the entire school population, the dean was looking to diplomatically transition Eigen off campus. In '71, Willis agreed to take him on in her office for 2 years to finish his schooling in architecture and supervise his work on internal R&D initiatives, which would ultimately replace his coursework at GSD. After completing his degree, Eigen was hired at WAI and promoted to Director of Research and Development. The Operations Research section, and the other piece at the USGS Canvas Geological Survey, provided the critical spatial mapping analysis and visualization output components for CARLA. But it was not a straightforward deal to negotiate. The USGS was a not-for-profit government entity, so special arrangements were made to facilitate their relationship with WAI and their research products and technical support contributions to CARLA. To add further complication, their own R&D was very much in process simultaneous with CARLA's. So ultimately, WAI worked with Kansas on and off from 1974 to '79 in the development and integration of their Surface 2 software, which became kind of the geospatial component of CARLA. So, quote, with the plotting program and planning units in hand, Eigen wrote the code to allow a series of analog and computational protocols to interface into a comprehensive planning platform. It also became clear that spatial analysis could increasingly accomplish a variety of tasks that were somewhat mundane for the architect, such as assisting in the solution of fire safety layout and other building codes compliance operations at the building scale. So we've got both environmental and building scales at play now. WAI soon realized that they could program planning units as planning modules defined in mathematical terms for computer use, which became one of the basic tools used in CARLA. They encompass not only elements within the building, construction envelope, but also elements within the immediate environment. Planning units could be any building program or site type, lot subdivision, for example, or any structural system. They were comprised of a number of stories, square footage, and other attributes such as numbers of rooms and parking per unit. Eventually, the firm had over 3,000 pre-programmed planning units in its database, with the additional capability to program an existing successful unit that the client provided. Ultimately, the planning unit pushed critical decisions regarding density, construction costs, and marketing amenities, including design, to the forefront of the design process, greatly reducing the time required to do large-scale residential planning. By 1953, By 1953, WAI had a partial version of CARLA up and running, but it was not without friction. Willis was running an office comprised of about 35 designers and 3 programmers. As the computational aspects of CARLA began exerting more of their influence on the design process, the interface between computer and the more traditional design processes, which most of the office was only versed in, needed to be addressed in order to keep the office working collaboratively. So once again, Willis leveraged systems analysis to deconstruct the often intuitive process of land planning. This meant working with each member of the firm to determine how they saw the planning steps involved and to document an overall systems approach to which all could agree. This resulted in a 3-step approach which integrated site and building issues at each step. And I'm gonna play, I hope. Uh-oh.
Oh, I think it's DVI. You might not need to.
Will it? Okay.
You might have to play, yeah.
Let's see if it will do it. Can you hear that?
It's not that one.
It's not this one?
No, the green one.
Okay, sorry, this might be painful.
And less expensive foundations. CARLA helps the planner create better environmental design by aiding in minimizing the amount of land used for roads and buildings so that open space is preserved. The CARLA process is based upon a planning unit that can be manipulated by the computer. Planning unit characteristics are always the same: the type of structure, number of bedrooms and baths, if it is intended for housing, the number of stories, square footage per unit, parking, and the like. However, the planning unit might represent any type of building, hospital, office, school, or any unit of planning desired, a subdivision lot, or 10-acre estates. In the CARLA process, the computer is used to aid the planner and designer. It does not make decisions for them. It does substantially aid the designer and our client to develop more creative ideas in a shorter period of time. Would you believe 6 months' work in 15 days? We think of the CARLA process as being divided into 3 general steps. The client supplies us with the initial project information: an accurate topographic map, a soils map, marketing and user need criteria. In conjunction with the client, planning units are selected from our databank of 3,000 planning units or designed to meet the specific needs of the project. Planning units can also be made up of successful plans previously used by the builder. In the first step, using the computer, we do 2 things: map the physical and environmental characteristics of the existing site, and through our planning unit analysis program, we select the planning unit most applicable for the project. In step 2, we cost the selected planning units to determine which building types meet the construction budget. Concurrently, through a computerized analysis we call site area allocation, we determine which areas of the site are best suited for various land uses, open spaces, recreation, and so forth. We then merge the appropriate planning units with appropriate site areas through a program we call massing of alternative configurations. The result of this step is a series of 20 to 30 development concepts. In step 3, a development concept is selected for final costing. In order to determine site development costs, it is necessary to determine quantities of earth movement and to schematically develop utilities. Site development costs are added to the cost of the planning units, resulting in total estimated development construction costs. If these costs do not meet the budget, new development concepts are tested again and again until the budget is met and the builder is guaranteed a financially feasible project.
Let's take a look.
Okay. So I am running a little short on time, so I'm going to skip forward here a bit. Whoops. Sorry. Okay. So just quickly, this is the printout of the massing of alternative configurations, just so you can get a sense of what they were looking at as designers. And then on the left was kind of their sequence of programming units that they were using. This part is funny, so I'll keep it in. So basically, Eigen produced an internal computer manual for the non-specialist for the office that was meant for professionals who had recognized the usefulness and importance of the computer for an effective and responsive fulfillment of his professional task, but for whom the computer is no more important than any other tool modern technology provided him with, such as an electric eraser, the Xerox machine, or the electronic calculator. And as you can see here, he has some interesting takes on the computer. It's a 48-page document, and it's pretty awesome. This in itself, I think, could be a paper. But basically, to shortcut here really quickly, in May of '73, Kaufmann and Broad, a very large real estate development firm, awarded Willis and Associates their first commission employing CARLA technology to do analysis toward the successful completion of the Crestview Homes project in Hayward, California. They had purchased the land from another developer who had sold after spending 18 months in a traditional planning process, which did not yield a project within budget. They were looking to build 120 townhomes on a 20-acre sloping site with a 35% lower budget than their failed competitor. Unfortunately, the project was never built, and I have some writing from K&B as to why, but what it did do was, kind of really prove that that CARLA could. It was a proof of concept essentially for CARLA, and it would result in the Aliyamanu project, which was literally and metaphorically a volcanic situation. Sited within an inactive volcanic crater that was previously used as a massive bomb and shell dump during World War II, the crater walls of the site both cradled and separated the community from adjoining areas. Ammunition-stored caves had been carved into the steep slopes surrounding the valley, and only one crater wall was gentle enough to be built upon. So it was a very complicated site, and these are some of kind of, again, the interface between the environmental work that WAI had done and CARLA to be able to produce things like a drainage map that was totally reliant on the computer. So thanks to CARLA, WAI's design required 40% less cut and fill than the previous firms. And needless to say, it was a really big success, a huge project on a super, super tight time frame that really wouldn't have been possible without CARLA. It was, Beverly Willis's kind of systematic approach really helped lubricate the relationship between the Army Corps of Engineers, which was difficult. And so, while the project pushed all involved to their limits, the toll was perhaps most severely experienced by Willis herself. As a woman at the time, there was more than just her firm at stake in the success of the project. After Aliyamanu, the firm continued to attract projects that leveraged CARLA's unique strengths, such as the IRS's new computer centers, but Willis began aggressively pursuing a different type of client whose projects were smaller and required a more aesthetic focus. She says, quote, "I never packaged CARLA for sale as a program, as planning and architecture firms were not using computers. Consequently, I thought there was no market. The developers who built multifamily housing, condos, and rental apartments were CARLA's primary market. However, in the late 1970s, this market dwindled out. Land suitable for single-family homes could easily be subdivided without need of a computer program like CARLA. This was also an area that predated the desktop computer, so any investment in plotting systems, later known as CAD, were then substantial. A market could have been in large engineering firms, but I was too unsophisticated to know that then." So, and I guess to kind of bring this back to conversations related more directly to the conference, as opportunities presented themselves, WAI choreographed hardware, software, and novel architectural design processes into CARLA, which ultimately forecast and rehearsed three significant current modes of computational architectural production: systems design processes, data-driven design, and parametric design. In WAI's marketing materials of '74, CARLA figured prominently as a current space-age technology designed to address the complexities facing builders, developers, and environmental planners working in the '70s. At the time, it was significantly more efficient than analog production, minimizing risk, maximizing project budgets, and providing more client control. But ultimately, and I think this is where we are again today, as architectural processes have become highly driven by computation, is there's sort of a give and take between the interfaces between vision and code, hand and mouse, plotter and scanner, and that these rapidly evolve and co-produce design processes. So a reexamination of CARLA also asks us to consider current relationships between quantitative and qualitative integrations of complexity, transdisciplinarity, and client-user agency as our understanding of design processes and the determinacy of the dynamic co-creation of environment and built product interventions continues to evolve. Thank you.
Our final speaker is Jennifer Kaufmann-Buhler. Jennifer is an assistant professor of design history at Purdue, and she's based in the Department of Art and Design and affiliated also with the American Studies Department. Her current research is on the history of the American Open Plan Office, specifically focusing on the tension between the progressive idealism of the early promoters of the open plan and numerous problems and challenges that emerged along the way for architects, designers, furniture and equipment manufacturers, organizations, workers, and probably more people as well, as things unfolded and became mainstream. This paper is on the integration of computers in office design and is part of this larger project. Jennifer.
Cool. Awesome. Thanks, y'all. First of all, I do want to also say how awesome this conference has been. I've had such a good time and joined my fellow presenters, who many of whom said, I don't quite fit in here, which I actually have heard in a lot of these presentations, and I think that's a mark to the really great job that the organizers did in picking some really unusual and unexpected papers to be a part of this community. So I really appreciate that and really excited to be presenting. So here we go. So this image was taken in 2008 at the John Deere headquarters. The furniture is the original open plan furniture installed in the late 1970s when this edition was first designed and built by architects Kevin Roach and John Dinkaloo. You'll notice that there are a large number of computers visible in this image. You can see, though, that the computers, that these desks are not well suited, right, to the computer. You'll notice that there's a visible tangle of power cords and networking cables, enormous CRT monitors that take up the entire work surface, leaving little room for anything else, and a lack of adjustability in the workstations themselves. In other words, this office and its furniture was not originally designed with computers in mind. I want you to keep this image in mind as I'm talking for several reasons. One, it shows the long life of office furniture. Organizations do not invest in office furniture with great frequency. Once purchased, office furniture is expected to last a pretty long time, many years, in some cases, many decades, as in this case. It reveals that early systems furniture and early open plan offices were not designed with computers in mind. In addition to being poorly suited to supporting the power and networking needs of computers, these are also poorly suited to the spatial requirements of the computer. And third, it shows that early open plan furniture was not designed with computer users in mind. The furniture, again, is not adjustable or adaptable to the physical needs or the ergonomic needs of computer usage. So a number of scholars in a number of fields have considered the socio-technical impact of computer usage in the late 20th century, specifically examining the ways in which computer restructured office work and reorganized clerical labor. There's also been significant research on the design of computers themselves, and important work on the influence of these new office technologies on the structure and culture of organizations. So this project builds on this previous scholarship that focuses again on the integration of computers in the design of offices and office furniture. As new personal computers entered offices through the late 20th century, they were often being used in workstations that were never intended to support such equipment. In this paper, I will examine this interaction between the adoption of personal computers in office work and the adaptation of office furniture to support the equipment and its users. I argue that in the late 20th century, the integration of computers in American office design was messy and complicated, shaped by the diversity of computer equipment design, changing power and cabling in office design, changes in office furniture, and new ideas about ergonomics. So one of the really critical challenges of integrating computers into office space was the enormous power and cabling infrastructure necessary to support these machines. The large centralized computers used in the 1960s and 1970s were housed in specially designed spaces with dedicated power, even dedicated temperature controls to prevent those sensitive machines from overheating. Meanwhile, the main office spaces at that time were generally designed with the more modest power requirements of conventional office equipment in mind. In the conventional office of the post-war, power was typically provided through walls and interior columns, but these were insufficient in the new open-plan office in which interior walls were intentionally scarce. In this new type of office, architects and designers depended on additional power access through floor outlets or through power poles to bring the power down to the workstation from the ceiling. Most early systems furniture did not have any power or cable management built in. But by the mid-1970s, some systems furniture lines began including simple raceways to run cable through or under the partitions. But this approach to power treated the furniture as a means of organizing and essentially hiding the source of power. In fact, one of the central concerns of architects and designers at the time was not supporting the machines, but disguising the unsightly mess of wires and cables necessary to support the machines. Because personal computers were still relatively rare through the late 1970s and even in the early 80s, these early systems furniture lines treated the power needs of these new machines as an exception to typical office design rather than as a standard. The very first pre-wired and powered partitions, called ERA1, were developed by Hayworth in 1976. In contrast to the standard raceways, floor systems, and power poles, the ERA1 featured pre-wired partitions that allowed power to travel in any direction through the linked panels. By including pre-wired circuits and grounded plugs, the Hayworth ERA1 created a new, more reliable and flexible power infrastructure for the office. The inclusion of dedicated circuits and grounded plugs is a critical change in that it shifted the partitions from pathways for providing power through the office to a direct source of power. The ERA1 could connect with power from the floor, a wall, a column, or the ceiling, and because the panels were pre-wired and contained integrated circuits to manage the power, they did not run the risk of overloading. Other office furniture manufacturers soon followed suit and created pre-wired, grounded panels with dedicated circuits for computer equipment. Early generations of these types of panels typically had two circuits, one for computer equipment and one for task lighting and other light office equipment. But by the late 1980s, these partitions increasingly had 3 or even 4 circuits to give greater capacity for computers and their numerous peripherals. While systems furniture lines evolved, individual offices that had purchased earlier configurations of systems furniture that did not include power continued to struggle with the issue of power and cabling, even as computers became more common. In other words, the development of powered partitions did not magically transform the millions of offices that had not already invested in simple furniture that didn't include power or cable, right? So even those offices that had invested in early iterations of these powered partitions would have found them insufficient to handle the power needs and cable runs required to support an office full of computers as that increasingly became more common. Through the 1970s and early 1980s, personal computers did become increasingly common in American offices, but they often arrived in a rather erratic manner. In contrast to those large mainframe-style computers, which of course required huge amounts of planning and enormous investment, personal computers were inexpensive and easy to purchase and install at the unit level, and they were therefore often acquired without much oversight and without significant organizational planning. As a result of this irregular acquisition process, it was not uncommon for an office in the 1970s or 1980s to have multiple office computers in use of all different makes and models and running different types of software. Some organizations, like the state of Wisconsin, even believed this miscellany of computing equipment was healthy since it avoided being locked into a specific computer manufacturer. Supporting this miscellany of computer equipment was made more complicated by the fact that computer design could vary enormously, not only across computers made by different manufacturers, but even among computers by a single manufacturer. And here, of course, we have the Radio Shack catalog from 1984, which I think just shows how many different varieties and types of equipment there were. Of course, the best way to experience this is just to walk downstairs through the galleries, right? And you can see all the different configurations and iterations. So this diversity of computer equipment and computer design presented significant challenges for architects and designers, furniture manufacturers, organizations, and their workers. So obviously, computers have specific base level space requirements. They need a work surface that has a large enough surface and weight capacity to support the equipment. As part of the design process, architects and designers had to survey that equipment in use and account for the diverse measurements to ensure that all of the equipment could be supported within the new design. This issue of providing adequate space was made even more challenging by the fact that designers often had to account for all the peripheral equipment that might also be used in tandem with a computer workstation. Among furniture manufacturers, VDT workstations increasingly featured the special VDT corner, which you can see right there, which was designed to optimally support the full depth and width of a very large CRT-style monitor. A traditional workstation might have a desk and a return set at right angles, but the VDT corner took advantage of the often unused or poorly used space in that corner of a workstation to create a pocket of space, especially for that deep CRT-style monitor. Though useful in VDT workstations, the design actually required more space than a conventional workstation and was often more expensive as well. While some organizations certainly had a large number of personal computers in use, perhaps one on every desk, as you see in this image, others continued to treat the computer as a shared device. These kinds of organizational decisions were built into the office itself, informing the kinds of furniture selected, as well as the overall layout. This was common enough of a strategy, the sharing of computers, that many of the major systems furniture companies produced multiple solutions to allow workers to easily share office computers. For example, here on their 1989 catalog for Unigroup, Hayworth featured a pass-through partition, that's right there, to allow one computer to be shared between two workstations. And other companies developed rotating lazy Susans that similarly enabled a computer to be easily adjusted to use in adjacent workstations, and that's what you see right there. So it spins around. Clever. In addition to the space challenges within individual workstations, the provision of workstations of sufficient size to support computer equipment also created space challenges in terms of the total office space. Each office has a limited amount of space that has to be optimally used for all the workers assigned to that space. Buildings and organizational demands often created additional constraints that might further limit the space allocated for the equipment. For example, many organizations had minimum and maximum space allowances for specific positions, ensuring, for example, that a manager would have a bigger workspace than a clerical worker. So finding ways to create workstations that would provide adequate space for the equipment without taking up too much overall space was a constant and recurring challenge. Office design was also expected to support the physical needs of computer users. As personal computers and other VDTs came into widespread use in office work, there was growing concern about the well-being of office workers who spent large amounts of time using these machines. Early research on workers' experiences using computers found that intensive VDT users were more prone to high levels of stress and physical discomfort that seemed to be tied to their use of the equipment. Workers reported significantly higher levels of musculoskeletal problems, including back pain, wrist pain, neck strain, as well as headaches and eye strain in tandem with their computer use. At the time, new research in the field of ergonomics focused on the perceived mismatch between the physical space of the office and the computers. It was argued that the conventional office was designed for paperwork, and the new electronic office needed to be reimagined to better support the use of VDTs by creating more flexible furniture that could adjust to the equipment and to the user, and creating new types of lighting that would limit the problems of glare. Office design was thus treated as both the source of the problem and the optimum solution. However, just as the diversity of computer equipment made specifying furniture to support the equipment challenging, that same diversity of computer design also made it difficult to design workstations that adequately supported computer users. In office furniture, decisions about the allocation of computer workstation support was often tied to the intensity of usage. Intensive users, which were often sort of using the equipment for 4 or more hours of continuous use per day, were thus differentiated from the occasional user, who was pretty much anything less. For the occasional user, the emphasis was often on keeping the computer out of the way as much as possible, while for the intensive user, the emphasis was on optimally supporting the primary task of typing or viewing the VDT. And I say or viewing because it was sort of thought that these were kind of separate tasks. Either you were someone who did a lot of typing, and then you didn't really need to be able to see the screen because you were a really good typer, or you were someone who didn't type, executive, and maybe looked at the screen, and then it should be at the screen at the viewing height, right? So these were seen as different tasks and requiring different spatial interventions. So, so this early division between occasional and intensive use informed the adoption of ergonomic policies in many organizations and determined the specification and installation of furniture and equipment. So for furniture users, for intensive users rather, a two-tiered desk was often recommended to ensure that the monitor and the keyboard were at optimum viewing height and optimum typing height respectively. Because of the enormous diversity of computer equipment, this type of two-tiered design usually had multiple configuration options to support different styles of equipment. Knoll, for example, offered a thin and thick keyboard drawer, right, to create that lower typing height, available with their Hanem Systems line, and you can see that here. But when the thick keyboard drawer was used in combination with a VDT corner, there was not sufficient room for the user's legs to fit under the work surface. And I really want you to think about that, because that's kind of a problem, right? So you know, this is a real issue. And the other thing I would just point out is that they actually recommended the keyboard support as being better for intensive users. The drawer was for occasional users, but the adjustable keyboard support was more than twice the cost of the keyboard drawer. So you could imagine, you know, bureaucrats, why don't we get the cheaper drawers, right? So I mean, these are the kinds of decisions. So for users, the messy interaction of computer equipment and office furniture left many operators using furniture or equipment that was poorly suited to their individual needs. For example, although it was recommended that the keyboard and monitor be at an optimum typing and viewing height respectively, that was only possible if the keyboard and monitor could be separated. The all-in-one machines like the Radio Shack Model 2 were still in production through the end of the 1980s and still being used in organizational settings into the 1990s. In those situations, the machine could either be at an ideal typing height or an ideal viewing height, but never both at the same time, leaving users either stretching their arms upwards uncomfortably to reach the keyboard or hunching their head and torso down to view the monitor. So computer furniture manufacturers had to thread a very, very fine needle, supporting the power and spatial requirements of an often diverse array of computer equipment and offering sufficient flexibility so as to support a diverse array of users. At the same time, architects and designers charged with specifying new furniture were faced not only with a complicated landscape of equipment and people, but also a crowded field of furniture lines with different types of solutions, as well as organizational restrictions that might further limit the cost or space allowance on specific furniture components. Yet the concept of a system meant that designers were often restricted within a particular manufacturer, in some cases a particular line of furniture, further limiting their choices. Thus, many solutions existed that in total could have perhaps met any given need, but no one system could optimally fit all needs. If the furniture line that the architect or designer was using had limited options for a certain type of technology or for a certain type of user, they were less likely to go outside of the system to address those needs, but rather would make do with the options in that given system to ensure a visually appealing and orderly office. Further, computer equipment and furniture were selected and purchased independently and often out of sync. Even in situations where the furniture was designed around immediate equipment needs, future changes in technology could render that furniture obsolete in terms of its technology or user support. Although office furniture was often portrayed as a solution to the power, spatial, and ergonomic problems of computer usage in the office, each iteration of office furniture was built around certain assumptions of equipment design and use that directly informed the way in which the furniture was designed, selected, and installed. Finally, the choices about the present and future of office computing that were made in the 1970s and 1980s have had a lasting impact on office design. The long life of office furniture and office spaces meant that the decisions about the allocation of power, as well as the size, shape, and configuration of workspaces and work surfaces, and the implementation of ergonomic support continued to inform the installation and integration of computer equipment for decades beyond the original installation of office furniture. Even today, the legacy of these choices create continual limits and challenges for architects, designers, manufacturers, organizations, and users as they continue to struggle with office design and furniture that is poorly adapted to contemporary technological needs. Thanks.
All right, I'll start. I was the I was the IBM branch manager in Madison, Wisconsin, who had to fix that problem with the government having too many different vendors and so on. It turned out to be a wonderful opportunity. The first year I was in Madison, we sold $10 million worth of PCs, so I'm grateful for the problem. But interesting enough, to your paper, obviously this is a period that I lived through as a manager. One of the interesting things that went on was that the employees were very influential in dictating the fashion of office furniture, and a lot of office furniture vendors appealed to them as opposed to the office manager who actually made the decisions. In your work, did you find any evidence of the role of individuals because of their propensity to use one type of computer versus another, or because of the style of cubicles or what have you, the period?
Yeah, absolutely. Oh, sorry. Talking in the mic. Is that working? Well, anyway, yes, to your point, absolutely. There was a lot of interest in having individuals involved, and there was this kind of, it was very hip, especially in the 70s, 60s and 70s, to involve the workers, right, in decisions. And so they would often do mock-ups of furniture and invite people in. Invite people into, thank you. Does that one work? Maybe? It's all good. Invite people in to, try out some different styles. Sorry. There we go. It's happening. No, it's okay. Oh, there we go. Oh, we're on. Oh, okay. So yes, all this is to say yes, absolutely. There was a lot of that. It was very hip. But I will say that there was also, my research has found that was, they were given voice, but their choices were not necessarily taken. So there was like an opportunity, but not necessarily sort of full inclusion of their actual preferences in that process. They were just given an opportunity to say, yeah, we like that one. Yeah, this one's cheaper. We're going to go with that one. So.
Hi, thanks. I have a question for Jennifer. And pardon me if you may have addressed this earlier. I kind of came in the middle, but I've looked at the emergence of like home computing furniture and got kind of from a similar period, and particularly the way that people would talk about them in computing magazines of the time. And what I found in personal computer use was that there was this tremendous kind of habit of hacks that people came up with, right? So they would write in and be like, I have eye strain, what do I do? And someone would write in and say like, put a warm cloth over your head for this long, or like buy a piece of plexiglass and put a piece of like saran wrap over it and it'll cut down on glare. I was wondering if you had found a similar kind of habit of people trying to retrofit these machines or their furniture to make them work for them in these environments?
Yes, they did. And actually, there's great stuff like that. Actually, the ergonomic manuals at the time often recommended these kinds of hacks because who was going to invest in new furniture yet again? Many of these companies had just bought furniture. They didn't want to buy new furniture that was better for the computers. So they were doing things like you would see people making makeshift hoods for computers. Like they would get a box and sort of cut it open so that it would reduce the glare because of the glare problem. You would see people, getting a block of wood to get the monitor up higher if they didn't have a two-tier desk. So all kinds of those kinds of fixes that were kind of workarounds. Absolutely, yeah.
Actually, this is one more question. I mean, having had worked for 20 years in open office environments and suffered their curses, I was just wondering, with computers offering more and more connectivity so that we don't actually have to be face-to-face, have you noticed any sort of inverse? I don't think it's actually happened, but it occurs to me that maybe it might have, is that as there's more ability to sort of connect, not being face-to-face, has that encouraged a move towards more private office spaces instead of open designs, or is there no real relationship between those?
That's a great question. So I always say there's not much relationship in the sense that, and as I get a lot of people talking to me about the horrors of the new open office, right, which is the office with no walls. And in some cases, the office with no territory, where people are sort of these nomadic white-collar workers with their laptops who sort of float around in these offices. And those and there's actually a long history of that. It actually predates. I mean, a lot of people think about it as very, very new, but the first hoteling offices were the early 90s. Hoteling is the office design term for that nomadic white-collar life. And so, I mean, I think to your point, I think there's this constant sort of issue of communication, wanting to support communication. And that goes all the way back to the 1960s when the open plan first came out, this idea of how can office design facilitate communication. And I think that that belief or that desire, that kind of holy grail, is still part of sort of current office design. We just keep cycling around as to what that looks like. So sometimes in the 80s, for example, it was found that people preferred more enclosure, which is how we got cubicles. The walls came up because it was found that environment and behavior research found that people communicated better if they perceived more privacy. And then later on, people didn't like cubicles. Cubicles started to become, sort of the office space symbol of like miserable white-collar worker, and nobody wanted those anymore, and they came down, right? Oh, they inhibit communication. And now people are like, oh, now I see why those cubicle walls were there. I kind of, it's too open. So I think we have this interesting kind of swinging. And I think a really interesting example of all of this is the decision at Yahoo to make people come into the office more, right? Doesn't anyone remember this, where they changed policy because they didn't want everybody telecommuting? Oh, that's bad we need people to be in physical space. There still is this belief that there's something very important about physical face-to-face contact.
So my question is for Meredith, and I guess one clarification question and then sort of a broader one. And so the clarification was, you showed one slide where there was like a floor plan, and I guess my question was was that floor plan it was like a home floor plan? It looked like, was that designed by CARLA, or was that sort of created by a person? And then I was just sort of more generally curious if you knew any of like how CARLA did its thing, like sort of what kind of algorithms or what sort of mathematical techniques it might have been using to do these optimizations. So.
Yeah, I did edit a good piece of the technical out of the out of the talk when I realized I was going over. So to get to your first question, the planning units were designed first by architects, but even I think in order for them to generate 3,000, it was a pretty algorithmic manual kind of endeavor. And then and so the drawing that I showed was kind of what they probably would have been designed by hand at Beverly Willis's office, and then someone would have input them digitally using a CAD program. There was probably like one person who was doing CAD in the office. And then from that, Eigen was taking measurements and converting them into basically code so that the computer could then do a number of optimizations. And then things start to get more complicated from there. There's kind of, in terms of algorithms and coding and the software side, the geospatial is kind of one set of logics that they were using a lot of matrices, and there's a whole kind of branch of coding or mathematics. It's sort of a bridge zone called map algebra that was actually initially worked on by Dana Tomlin at Yale at the forestry school, and then had kind of a weird trajectory, and some stuff was getting picked up and pulled out at Harvard at the GSD lab, but Harvard wasn't the only place that this was happening, and so there were kind of some of those maps that I put up, and again, I didn't go into detail, but as far as I've been able to trace, those were all the sites in the world around that time where any coding related geospatial coding was happening. And then on the more kind of algebraic side, I guess I would call it, but basically the side that Joachim Eigen was working on was a much more straightforward. I'm not a mathematician. I'm a really bad person to try to explain. I don't have proper language to explain the differences, but was less spatially driven. It was more of a, I don't know how to describe it, but just it wasn't using kind of matrix algebra. It was using more standard equations. And a lot of that work was, like the planning units had a spatial component, but it was relatively easy to map it into kind of more linear equations. And then certainly like the costing and whatnot was really straightforward to just do kind of more linear work on. So I hope that sort of answers your question. And I mean, in terms of the hardware-software interface, they were time sharing using 3 companies, General Electric, Timeshare, and one other one. So they were using a teletype machine to dial up, send the programs into the mainframe, then log into the mainframe, do the computation, and then the mainframe would send back via the telephone the final outputs. And I had like all the cost in there and stuff that I didn't talk about. But so it was kind of a crazy process, and then Beverly Willis really needed the input and output devices in office. There was really no place to kind of go locally to rent that. So there were some images of like these large drafting boards with these weird devices on them. So they would actually, in order to digitize like topos, they had this digitizer, and you would have to like trace by hand with this big thing, like every line, in order to kind of get the topos into a vector format. And then they had a big plotting machine. But even things like plotting at, like GSD, Harvard was working on plotting, which took them several years to get straight, not only with the software interface, but also just how do you deal with pens and ink and the mechanical, you need like X and Y axis, and it can't just be, the first plotters only did like, rectilinear form. It took them a long time to figure out how to get a mechanical device to do a curve, and I mean, it's just, it goes on and on and on, but hopefully that gives you some sense. Yeah.
Hi, sorry. I had a question for basically the whole panel. And I'm sorry if this is like kind of posed in an abstract way, but I'm sure you could like fill it in with all your great empirical stories. And the question is this, basically, like, if I think about history, the sort of like fundamental concept or thing that we're dealing with is time, but all of your talks had a really interesting like spatial dimension, right? Whether it's like network topology or like infrastructure or the environment or office plans. And I guess just like as a very abstract and open question, like, how do you guys deal with like the temporality of these spatial issues, or like think the kind of like space-time whatever relation in your like individual works or projects or things like that?
Hi, thank you. That's a great question. For myself, there's actually a dimension that might go in a longer version of that talk, and that's looking at a routing architecture. There's a kind of a rate at which nodes will communicate with each other to tell them, like, who am I next to and what has changed on the network. And that rate varies quite a bit for different kinds of architecture or different kinds of infrastructure, right? So on a fairly modern computer network, that would be, for us in human time, very fast. Maybe if you're talking about a network of ports for trade, if there's a storm or if something goes wrong in one of the ports, that like rate of updating would be much slower. So I've started to think more about like how, the temporal dimension of as a comparative point. Haven't really gotten into it yet, but I think that's an excellent like path in that area. So thanks.
I'm not sure this is going to answer your question, but it was the first story or anecdote I could think of. I took a slide out of this talk, which was a phrase that my friend Aaron Cope used in a talk that I made him give, so I like steal it all the time. And he said that history is time breaking up with itself, by which he kind of meant, history is that moment when like something happening in like a here and now and present kind of has to like partition out certain events, and those become histories. So like the history of Xerox PARC is computer history. The history of a Superfund site is environmental and labor history. Or that's sort of the way that kind of partitioning happens. And I think one of the things about kind of my like unhealthy tendency to like vision quest the shit out of everything is partly driven by like wanting to collapse all of those timelines and, sort of force time to reconcile its own breakup, as it were. So
obviously, I spend most of my time in architecture, which is totally preferences the spatial, to the detriment of time. And so I'm always actually working to try to get time back into the equation. And I think, and again, this was something that I didn't really explicitly unpack in the talk, but what was super interesting about CARLA was that, you know, they could map, like the caldera, for example, figure out roughly existing drainage, and then with map algebra equations for cut and fill, they could start to predict, and this is where the kind of co-production piece comes in a little bit, but what would take the least amount of grading, but simultaneously probably have the least impact on the environment, such that things would ultimately be more stable. And so they're dealing with spatial components that have a history and have a future, and they're trying to kind of, you know, capture the past in their present analysis so that they can forecast future to a certain extent, which is, and I'm still trying to get my head around this, and I'm also doing work in ecology, and there's all kinds of ways that ecology is trying to deal with like history too, which is really tricky to unpack in the landscape. Like, how do you read a landscape to understand what's happened before and since? And so I almost feel like, in a way, like we do space really well or we do time really well, but we're still having trouble getting them to really interface. And so it's a fantastic question.
Yeah, I would agree with that about the space and time tension. My work, I'm often trying to think about the ways in which, in design, I think there's this tendency to fix time, to sort of think that a certain design is from a certain period in time, and that's when it was done, and then the next year something new comes along, and everything else before that disappeared, or something to that effect. And part of my project actually is thinking about the idea that a space has a longer life, and that a space itself can evolve in terms of its design and its use and its meaning, and that we don't always need to think about the first origin, the first iteration of a space, that the space that we can think about change, and that is absolutely about time. But to think about change requires a kind of reimagining of the kind of priorities of architectural history and design history, which often privilege the maker over the user. So in order to think about the life of the space, we have to think about the lives of the users and the people who inhabited the space and maybe made changes to the space, which is completely antithetical to the way, for example, architectural history has traditionally worked, right? Which often like wants to talk about the original design, the original concept, right? So I think that messiness is exactly what interests me the most, but it involves sort of looking across time in some ways for me.
Any other last question? Yeah.
Thanks for the great talks. My question is mainly for Bradley. Kind of getting back to the historicizing question, I was thinking a lot about path dependency in terms of routing, and I thought maybe give you opportunity to speak to that. In particular, in relation, you kind of touched on transportation a little bit, and maybe I thought there'd be an interesting relationship there in terms of how some of these routing ideas reinscribed, of course, like previous transportation networks. I also thought maybe we could think about it in terms of your talk, kind of like path dependency in reverse or something. Like, what do you think is some of the attachment to necessarily like the impetus to reinscribe some of these networks in this kind of iterative like the attachment to kind of like technological innovation? Like, what do you think is the compulsion to necessarily, why is the previous network insufficient that we have to then kind of just reinscribe the network, but with this kind of, I don't know, maybe there's something there, but.
Yeah, thank you. I think there's my research so far has largely been on like proto-internet and then internet networks. So in terms of lineages in transportation networks, I wouldn't be able to speak to that very well at all. But I think that just as a way to compare between space and time, my kind of idea is that if there's like a routing logic, then maybe there's a way to use that logic to link comparisons where we might not have necessarily identified them before. So I think with the traffic system, that example is one in which where insofar as the things that are moving don't control their destinies entirely, then there's a routing architecture. So we're all unique people, but if we use that uniqueness to drive exactly how we like in traffic, the government will like penalize us like quite extensively for that. So there's a stoplight and there's an intersection, and that suggests a kind of roading architecture. And then like looking into the conditions of that, of the construction of that, and then so with this case of the telegraph, I think, you know, as I mentioned there, it's probably Bjorn talking to me about that got that idea in there as a comparison, as a comparative tool, and I think he'll be the one that goes and does that research more fully. But I think looking at and seeing the similarities then makes us think, well, what if there is like, you know, historical connective tissue? Where do you necessarily go and find it? So that's the kind of, you know, interesting point for me there. In terms of like what drives people to change, you know, I think capitalism has a built-in impetus towards some kind of innovation, although it, you know, for the 20th century, a lot of that's been funded by the government. But one of the, I think the kind of interesting flip side to that question is what compels us to claim radical breaks from the past whenever there's a change that, in retrospect, looks a little more iterative. So I think what's interesting to me is this: when you look at just some basic similarities between the telegraph system and the internet, we think about packet switching and then early internet stuff as this radical break from the past. There was nothing before it. All the communication was awful. And then we had the internet, which is great, even though it's awful again. So I think the construction of these, if we assume like lineages and path dependencies is a kind of normal fact of you know, life, the question is how and when does it get chopped up? I think is really fascinating as a kind of a social question. Thanks.
So one thing that I think is great about bringing design and history into conversation, especially thinking across space and time, is that it forces us to deal with normative questions. And I think you've all done that beautifully well. So it's time for a break. So let's thank our panelists.